All right. Well, hey, everybody. It's Dr. Nelson, and this is for my fall 2023 class. It is August 29th. It's Tuesday night, right before the hurricane is supposed to hit North Florida. So I say that only because I did accidentally put up a video from 2 years ago that some of you watched. So this is a new one. This is not that one from 2 years ago. And if you're watching this in 2025, this is the old video that you shouldn't be watching. Anyway, I was debating. I was actually kind of originally planning to do an announcement, and then I decided not to. And then driving home, I thought I would, because there were a couple of things I wanted to say today in class I didn't get to. I also, and I hate to say this because, to be honest, this is the last thing I want to do tonight. I do actually want to finish up a little section of the lecture so that we don't have to deal with it next week, because I feel like I'm getting a little bit behind. So you can watch this at any time over the next week before we meet again next Tuesday. And I do want to address a couple of questions and statements I hate when I don't know the answer. And I hate, at the very least, I usually anticipate a question. And so it's always weird when I get a question I absolutely can't answer. So it's been bugging me. So I do want to answer a couple of questions that came up in class today. Okay. First off, you do need to be, I just want to make sure that you do need to be reading William Cronin's Changes in the Land. It's still a few weeks before the book reviews due, but you should be starting to read that at this point. And we probably won't have a long class discussion, with 1 day a week. And I do have a lot of material I want to get through. I don't have a long time to discuss, although I do like having you guys talk a bit. In fact, that's one of the reasons I want to do tonight, so I have a little bit more time in class next Tuesday. But what I probably will do, and I'll do this with some of the later stuff we do, is I might kind of sort of like pretty much names out of a hat. I might call in 3 people kind of randomly to talk. This is a trick some of my professors did. And that way, over a semester, you kind of get everybody talking at least once, and nobody knows when they're going to talk. So you got to be ready at any moment, because what happens is, and you can already see it in this class, there's about 3 or 4 people that do all the talking, and everybody else gets real quiet. I was one of those quiet people. So anyway, so just make sure you're not putting that off to the last second. Really, the bigger thing to remind you, and I didn't say it today, is paper topics. They are due pretty shortly. So I do want a little write-up. So I do want you to be thinking about it. Feel free to shoot me emails if you have specific questions. I know I talked to a couple people today, for instance. Just a reminder, it does need to be a history topic. So, don't just be about something right now. It could be an issue now, but do the build up to the history, right? Like talking about lawns, even though they are a problem or can be a problem right now. But I was looking at how do we get to now, if you will? And as I said before, I really want to push you guys to doing topics, really, this is a history class, and this is a deep history class. So don't be afraid to do some big topics and go back a ways. Again, you can go more than just the 20th century, but there's also some great 20th century topics as well. I'm pretty wide open, but I might tweak it as you suggest things to make it more history. Okay. And one more thing, the lecture that's already online, I know a couple of you have watched it already. It's called Primates, dealing with this trilogy of women who studied primates, Jane Goodall, Diane Fossey, and Baruti Galdikas, looking at ape behavior in Africa and Indonesia. But they're also, that started out as a project of looking at human origins. And since apes we're essentially apes ourselves. And so even though these apes, don't go way back, they've evolved just like we have, but their behavior may mimic some of our ancestors' behavior. So trying to understand how they behave might help us understand ourselves. But it also gets into human-animal relations, something I go back to a lot in this class. And somebody brought up something that I didn't know about today, among many things that you guys will bring up I don't know about. Bunny the dog, I think that was the name, about a dog that has been taught a language, which was fascinating to me. I feel bad because I think I kind of shot it down because it brought up this issue of, can animals actually learn a human language? And sign language is a human language. It's an abstract way of thinking, and can another species actually cross that gulf? And it's a real debate. And so I was bringing that up, and I felt later, I thought I kind of shot down an interesting anecdote, and I didn't mean to do that. So the other thing, let me go ahead and switch screens here very quickly. So I can get into, as quick as I can, get into the lecture part of it. So I did have a couple questions today, and I did want to give a good answer for both of them. I know I didn't during class. The first one dealing with leaf blowers, about a specific statistic, and I was embarrassed because I looked at it and thought, oh God, I don't remember if that's the exact statistic or did I make a typo in it? And I was like, oh God. And as you can tell, I quickly, let's change topics. The statistic itself came from Ted Steinberg, the guy who wrote Acts of God. He also wrote a book about lawns. That lecture came from about 4 separate books on the history of lawns and pesticides. And but I could not remember exactly what the statistic was. I did look at my notes. That was verbatim from Ted Steinberg. But again, you do have to be careful. I have to be careful sometimes with environmental statements like that, because there is an activism element to it. And sometimes people are trying to make their case. And I've said this before already, sometimes they overstate their cases a little bit. And when you start getting into those kind of apples and oranges comparisons, they're always kind of an estimate anyway. They're never exact. But this, leaf blowers have always been something, since they came out in the early 70s, not only their noise pollution, but they are very dirty machines. Again, leaf blowers have been targeted quite a bit over the years, and to some degree, probably rightfully so. Somebody made a statement that, hey, cars and leaf blowers burn the same thing, so shouldn't it be exactly the same output? But again, it has to do with the type of motor we're talking about. For instance, like a 2-stroke motor, which is very inefficient. They only burn about 60% of their fuel, so a lot of the fuel is just released directly into the air. They really are, much dirtier than your average vehicle. And there has been a couple of studies, even in fairly recent times, making that comparison. Where Steinberg probably got his data, which is where most people get their data when it comes to comparing modern vehicles with leaf blowers, comes from a study by the Edmunds Group. In this particular case, they compared a Ford truck with a leaf blower. And in this case, they said it equals about a 4,000-mile journey. I had 7,000 from Ted Steinberg. But again, the connection of leaf blowers and really dirty pollution versus a vehicle, that does seem to be pretty strong science. Just how much we could debate, we should debate, I'm not going to get into, but that is where this data comes from. And the Edmunds study is the most common one that most people are quoting. So the point of the lecture today, building up to human origins, partly was to try to set the stage, talk a little bit about the land, some of the previous species, the fact that we had to get these species off the stage to make room for new basically the age of mammals. And also the kind of trying to make a quick point that what we're talking about today, the things that we have today, forest, oil, air, all of this are byproducts of the past. In fact, the reason we have oxygen is because plants were here first and they produce the oxygen that we now breathe. Oxygen, again, is a byproduct of plants that first evolved on Earth, right? So everything we have today comes back from the past. So in environmental history, we often do go back pretty far back sometimes to try to sort of tell that story, if you will. But I brought up dinosaurs, partly because they're fun to talk about for a moment. And I did bring up the whole idea of fossil fuels and, and the fact that the energy we use today comes from living materials from the past, including plants and microorganisms, and perhaps dinosaurs as well. And, somebody asked about, well, don't fossil fuels actually not come from dinosaurs? And of course, they don't come from fossils. And I did want to make sure nobody thinks they actually come from the fossils, because some people do think that. But then there's a little conversation about do oil maybe not come from organic materials at all? I had never heard that before. That's why I really was like, oh, well, let's just kind of move on, because I really don't have an answer to that. It turns out it is a question that has actually been asked. There has been some debate. Oops, I went too far. Sorry. There has been some debate about this, it turns out. And, people say, there's methane on Jupiter, there's methane in Saturn. So we do see some of these materials produced outside of, say, plants and animals, right? And in laboratories, they have been able to sort of show that this process could actually happen without, say, animal or plant life. But there's a lot of evidence, apparently quite a bit of evidence, that it did indeed, that there's a lot of markers that by and large, oil, coal, all of this does indeed come from organic materials. So it was interesting. I've literally never heard this idea. I think it's early 2000s was when somebody started first really kind of making these statements in peer-reviewed journals, and other people looked into it. The consensus still seems to be what I said in class. I mean, that still is kind of what most people are arguing at this point. So anyway, it's something like I've literally never heard that before. So, and I was embarrassed I didn't have a good comeback or at least a good counter explanation. So anyway, I learn from you guys sometimes. One thing I am always a little weird, and I thought this today when it came up, is sometimes when sort of kind of consensus ideas are challenged, sometimes I'm always like, well, where is this challenge coming from? And again, when you start getting these kinds of issues, sort of like the critique of Rachel Carson from a chemical plant, a company, you do see this, and as I was looking up some graphics for this little bit here, this popped up, plastics company. We're going to talk about plastics quite a bit later in this course. And of course, they're arguing, that, plastics, of course, are petroleum, but petroleum are natural. Here they say not dinosaurs, but other organic materials. Therefore, plastics are actually natural. So we shouldn't be attacking plastics because they're actually natural. They're part of the biomass of the planet. I mean, they're right. Everything, because we don't actually create matter; we just transfer it, right? Same with energy. But again, I think it's a pretty large leap to say that plastics are just literally nature. But anyway, but it is an interesting question about the oil thing. And like I said, it doesn't seem to be the consensus at this point, but it is a real question that people have asked, and that was new to me. Okay, so again, repeat a tiny little bit because I kind of got off course right here at the end, and then I ran out of time. So one of the arguments that I was trying to make about dinosaurs, and really not just dinosaurs, but a lot of the species before us, is we often use the term dinosaur in a negative way. That's out of date. It's a dinosaur. It's useless. Move on. When actually the age of dinosaurs is an era of real success, if you stop and think about it. I mean, if you think of the time range that dinosaurs existed, you're talking over 200 million years ago to about 65 million years ago. And again, it really was a traumatic event that ended it. It wasn't like they died out from, not being able to adapt. It was literally this traumatic event that led to the mass extinction. And if that had not happened, the rest of the story we're going to talk about probably wouldn't have happened. So that's why I was saying one of the biggest things dinosaurs did is they got off the stage, if you will. And again, the hypothesis going back to the early 70s was that Earth was struck by a major meteorite, which has happened many times in our past. We know even from the 20th century, even relatively small meteorites can cause massive damage. And we also know from physics and such what could happen if a celestial an asteroid, I don't know, I'm getting all proper there, an asteroid slammed into the Earth, it could cause massive damage. And in 1981, Walter and Luis Alvarez, his father and son Italian team, are the ones that really began to really build the evidence for this case. And it went from being a hypothesis to an actual theory. And it's still the accepted theory as to why dinosaurs and some of these other animals and plants at that point were no longer with us. It does seem to be a little bit of climate change even before the asteroid may have been playing some role. But this seems to be the tipping point event. The asteroid acts as a name, Chicxulub. It's a Mayan word. It means tail of the devil. They even know where it hit, just right on the edge of the Yucatan Peninsula, pretty much forming the modern Gulf of Mexico. So, and I am going to cheat a little bit, make sure I get the numbers right. The estimates are that it hit it's about 6 miles wide, maybe about 10 kilometers wide, thereabouts, slamming into the Earth about 25 kilometers per second. Of course, I mean, this would have just literally lit up the sky, for about half the hemisphere. It would have burned so brightly. To give you an idea of this, I know you can barely see me. I'm on the little screen. And of course, I don't have what I'm looking for right in front of me. I'll just use this. So when you look at it in the sky, like a couple of weeks ago, you had the Perseids meteor shower. And I saw a couple. And you see something very bright shoot across the sky for a second. It looks like a little, like a little white line. What you're looking at is a piece, a meteorite, and I know you can't really see it, but about the size of an eraser on a pencil. That's about the size of most of the things you see in the sky. As they're coming through the atmosphere, they're burning up very brightly and then just disintegrate. And again, you're talking about something so minuscule, and yet we can see it all the way down here, brighten up the sky. Imagine something 6 miles wide coming through the atmosphere that fast. And it's, of course, most of it's going to be burning up as it's coming down. Just that alone, just imagine the sight of that, the impact of that, and then slamming into the earth, something that large slamming into the earth. And again, as I said in class, we called this a nuclear winter because it would have been similar to what would happen if we exploded many of our nuclear bombs all at once. We would see worldwide tsunamis, winds maybe as much as 600 miles per hour around the impact site, blowing out. The Bear Paw Sea, the sea between the two mountain ranges of North America, would have literally emptied into this crater, a crater that would have been about 180 kilometers wide. I've seen different estimates, anywhere from 5 to 15 kilometers deep. So again, water rushing down from the Bear Paw Sea would have filled that up. And then, of course, the remainder of the water would have turned into tsunamis. Again, that just gives you some of the idea of what this would have looked like. I showed this today. This is the Behringer crater, about a mile wide. Again, we're talking something that is, 100 times this width when we're talking about the Chicxulub crater. But this is a relatively small meteorite that struck, but yet this would have caused major damage. Not global damage, but definitely regional damage when it struck. Some of the evidence that these spirals, we're talking about these actually right now because I don't know if you guys know about there was a weird thing that flew through the solar system not too long ago, and some people have estimated that it could have been an intelligence design. And there's some spirals from that that people have found that they think it might be evidence of it. So anyway, this is basically melted rock. This has to do with both coming through the atmosphere and the crater impact of this. And this is some of the actual physical evidence of this meteorite. If you actually look at the top of the Yucatan Peninsula, you can see what are known as cenotes. I've actually been to Yucatan, and they're basically like sinkholes. Essentially, they're really quite amazing. For Mayans, these would have been sacred sites, so a lot of archaeology has been done on these because bodies have been dumped into these cenotes and all kinds of offerings to the gods. So archaeologists love these things, and for tourists, they're great places to swim and such. But you can see there's a whole line of these cenotes that actually are kind of outline where the crater would have been. The rest of it being in the Gulf of Mexico. This is an artistic kind of reconstruction, kind of giving you a sense of the size of this. There was actually a pretty interesting movie, turned out to be pretty lousy in the end, about a guy going back in time, and he's arriving like a week before the meteorite would have hit. Thought it was a brilliant idea. Terrible movie. It actually wasn't a very good film, but it was a good idea because I really thought they'd really do a good job of recreating what this would look like. They didn't. They lost opportunity. Sometimes kind of the KT layer, this boundary, if you will, kind of marking the change. It's also known as the iridium layer. I mean, this is a layer found throughout the Earth at the same point, about 65, although I have seen 66 million years ago on some sites. That is kind of the actual physical evidence of part of the physical evidence of this meteorite. In fact, this was the original evidence that the Alvarez family first used, and then the crater and then some of these other pieces of evidence have gone into place there. I mean, you can see outcroppings of it, especially out west, which is kind of amazing to think about. You can go and literally practically touch, in a way, the thing and the evidence that led to the destruction of dinosaurs. Anyway, so I remember when I was a kid, I was really into dinosaurs. And we used to be told as a little kid, you read books, and they just talked about the ice age coming, and then mammals eating the eggs of dinosaurs, and the mammals basically outcompeted the dinosaurs. There is some evidence of that. I mean, after the meteorite struck, there was massive climate change, and we do begin to see mammals begin to rise. But actually, in the years after the dinosaurs, the actual dominant creatures for a brief moment were turtles, of all things, not mammals. So what a boring movie that would have been, The Planet of the Turtles. But animals like the alligator snapping turtle do date back even to the time of dinosaurs. And again, they look like it, don't they? Let's jump way ahead. Let's jump about 63 million years in the future to something known as the Pleistocene era. the Ice Age, which again, most people kind of lump this together with the end of the dinosaurs, even though they're completely separate. The Pleistocene era, also known as the Ice Age, goes all the way up until the human era. And this is really the time that human origins and even Homo sapiens, you and I, emerged, was during the Pleistocene era. In fact, it's really interesting if you start looking at what the world would have looked like during the Ice Age, where the continents would have been pretty close to where they are today by this point. They've moved quite a bit from 180 million years ago. But again, these continents, to a large degree, would have been connected through tundra and ice. The sea levels would have been much lower, so there was a lot more land exposed. Florida would have been about twice the size that it is today, for instance. We know that Asia and North America were connected by the Bering Land Bridge. But so exposed land mixed with ice, really, some people have said this is the lost continent. There was kind of almost like a wholly different continent that no longer exists because it literally was covered up by water and melted away when the Ice Age ended. So again, coming out of that fifth great extinction of the end of the dinosaurs, you get into the Pleistocene era. And again, Pleistocene going back meaning recent era. Of course, we are now in the Holocene era, which means basically the current era. We'll talk about this another day, but there is some debate whether we should either rename the Holocene era, the Anthropocene era, the era of humans. Some people have said, well, the Holocene era should end at the beginning of the Industrial Revolution. That's been one theory. Another one, and I actually like this one, that the dropping of the first atomic bomb, because that's such a distinct moment, that should be the beginning of the Anthropocene era. Again, these types of things take a long time to go through. You have to have all these people agree, but the Anthropocene era does seem to be on the way to being adopted. Just when do you start it? So anyway, but we're still in the Holocene era at this point, but the era right before this was Pleistocene era. We talk about the Ice Age, but really it was a series of ice ages. It was a time of ice forming, and then it warms up and the ice melts. We call it retreating, but really the ice just simply melts. And then maybe 10,000 years go by, and then it gets cold again, and the ice forms again. And then maybe after 40,000 years, that ice melts, and then it starts over. Another warming period, and then the ice forms, another 40,000 years. And this happened dozens of times. So it's not just one ice age. But during this period, this is, when our ancestors came about. And us, this is the era we come about. It's also the era of megafauna, which just means big animals. And we'll talk more about megafauna when we get more into Native American history. So this is the age of mastodons and mammoths and giant saber-toothed tigers and giant sloths and giant armadillos and things of that nature. So how do we know this? I mean, this is really kind of the part I wanted to mention very quickly. How do we know what we know? And again, I'm a historian. I know I'm going to use that line a lot, so I'm just using this data to just tell the story. But how does this data come about to begin with, especially when you're talking about weather from 1 million years ago? How can we know this stuff? And of course, it's always going to be incomplete data. We're never going to have a full story unless we can be, like 65 million, the movie, and we can go back in time, right? Anyway. One of the things we use, of course, is weather instruments, thermometers, barometers, things like that. But the reality is, for the most part, we're really only talking about maybe 200 years. And that's not everywhere. Even within the West, Europe, and what is now the United States and Canada, even that we only have, people are only using these things in certain areas and at certain times. So it's very incomplete data, but we definitely have that. Then we have ice cores. Literally just pulling out long pieces of ice. And some of these, hundreds of feet long in some cases. In fact, FSU, right down the road from me, because I'm just outside Tallahassee right now, has one of the best collections of these ice cores that they've pulled these out and then kind of chopped them up into smaller, more manageable cores. There's a tragic story about 15 years ago where they actually had a power outage. I'm not sure if it had to do with a hurricane or not, like tonight, but there was a power outage, and actually the generator didn't work, and they actually lost some of this ice. Some of it melted. I can imagine walking in and just seeing water and realizing you just lost millions of years of data. So what's kind of amazing about how ice sheets work, and of course we call them ice sheets because they're very relatively thin. I mean, they may be a mile or two thick, but it can be thousands of miles wide. So like a sheet on a bed, right? So it's not just, we kind of idea that it's just ice and this ice moves around, and it does move. But what really forms these ice sheets is falling snow for the most part. So the snow falls and it slowly accumulates. And then again, it freezes into ice. So as the snow is falling, first off, other things are getting trapped, microscopic pollen and other organic materials that's trapped in there. But there's even tiny microscopic pockets of air. And if you cut into these cores and you have the right instruments, for just a fraction of a second, you can capture that air. You can measure, quite a bit of material in that air. Now, again, I'm not a historian. I can't get into too much more detail than this, but they are able to capture a lot of data because it is air from 50,000 years ago, 100,000 years ago, 1,000,000 years ago in some cases. And it's still that same air that's been trapped in this ice this whole time. That's why it's, again, if it melts, you lose all that data. It wasn't until I started looking into this, I realized like what it is they're doing. And again, a lot of it is looking for these little air pockets. They're also looking for other organic materials trapped in this ice. So that's one, but even, and it does tell us a lot about climate and types of plants that were living at that time. And again, we're getting them from the poles, but other areas where ice still accumulates. You also can get deep sea cores, the same basic idea, but instead of ice, you're getting sediment buildup in the bottom of the ocean, right? You can also do it where oceans used to be, like the Bear Paw Sea. Same thing, you're getting buildup of organic materials and minerals and all this sort of stuff. And pollen, that can tell you what type of plants were living. That gives you a sense of what the climate might have been like. Pollen itself, I've mentioned it a couple of times, both from the ice cores and the sea cores, but from other areas as well. So pollen studies, what types of plants were alive at this point. Again, we know what types of plants need what type of weather, whether it's wetter or drier, gives us some sense of the temperatures and the climate of the time. Tree rings, dendrology, in other words. Again, trees do produce a ring pretty much every year. These rings can tell you data about how wet or cold it is, how much growth is happening. And there are databases going back quite a ways of tracing these tree rings around the world. When, say, you discover a fort from, I'm kind of making this up, but if you have a particular fort that when it was built, so when those trees were cut, then you can backtrack from that date and count back. Oh, this has 50 rings. This is 1402. We know that this tree is 50 years old. So then we could go back to 1352. And by using that data, they actually do have these quite amazing dendrologic charts. One of the most amazing statistics is that pretty much for every decade of modern human existence, meaning since maybe 4,000 years ago, there's at least one shipwreck, and there's actually many more in many cases. And of course, those ships are going to be made of wood. They can use that wood to help do this. So again, as people are doing archaeology, this is one of the things they're looking for. This is much more helpful, say, in the last 1,000 years than it would be for, say, 10,000 years ago. But this, again, just another one of the ways that we're trying to recreate this weather data. And then, of course, you have other types of records. Farmers are great at this. A lot of farmers keep journals. They talk about rainfall. They talk about temperatures. They talk about the types of crops they're growing. So again, journals are really great for this. Letters. Again, you're not going back to the Ice Age with this. This is more the last 400 or 500 years. Even things like paintings and works of art. They're drawing plants, they're drawing weather, they're drawing landscapes. And, a botanist can go, oh, if that tree is growing, that must mean that's this type of climate versus that type of climate. So again, putting all of that together, it is an incomplete picture, but we can get some sense of weather from the past. So I guess let me give you a sense of how people are putting this data together. And then we historians come in and go, great, now I'm going to write my book using your data. So getting back to these ice sheets during the Pleistocene era, again, they're relatively thin compared to how wide they are. But nonetheless, you're talking a couple of miles, and in some cases, even more than that. They're retreating. Again, what we really mean is the melting of the ice. Some estimates are maybe 20 times this happened. I've seen even as high as 60 times that we see these retreating. And think about, just look at North America. We've already talked about the Great Plains. This is also adding to the Great Plains and some of the other farmlands. So as this ice is forming, it does indeed move. It just like continents move. It does move and float. It melts a little bit. It moves a little bit. This ice is forming, and it is bringing nutrients with it. Also, nutrients are being trapped by the snow. And when it retreats, again, what that really means is it melts. All that stuff trapped in the ice just literally gets left behind. And because of these mountain ranges in North America, a lot of that ice is kind of being directed into that Great Plains area, and then it melts, and then it comes again, and it melts, and it keeps doing this and doing this. Again, just building up the nutrients in places like the Great Plains and parts of New England. It's also, as this ice is moving, and of course it's bringing with it often rocks. Sometimes you'll just see these random rocks in the middle of nowhere. Well, that's often the product of the Ice Age. Because geologically they can figure out, like, oh, this rock originally formed 500 miles away, but here it is located here. This was being transported by these ice sheets. But as it's moving, it's also crushing rocks, what we call loess. And this is one of the kind of foundations of soil, essentially. This is some loess bluffs from China. But we have them here as well. And again, these are the remnants from these ice sheets. And again, what we're seeing is the beginning of a lot of modern day soil. And again, this is getting back to creating of the Great Plains. And that takes us up to maybe about 18,000 years ago, which is when humans start coming over to North America with what we will later talk about, the Paleo Indians. But before we get to Paleo Indians and Native Americans, we kind of skipped a step, didn't we? We talked about dinosaurs and we talked about the Ice Age. Now we're talking about 18,000 years ago. It's like, wait a minute, there's a piece missing. And that piece is what we're going to talk about next Tuesday. That's us. How do we get here? What's our connection with nature? What's our connection with the natural world? How, and as I asked you in class today, where does nature stop and we start? And that's what we're going to talk about next week. All right. Thanks, guys. I appreciate it. If you're watching this on Tuesday night, which I'm sure you're not, be safe. Anyway, I'll see you guys next Tuesday. Okay, thanks, everybody. As I awkwardly end this.